skills. His goal is to guiding everyone with his knowledgeable values and got achieved in this. He also published 11 international journals and 6 national and international conferences. His research field includes investigation on reduction of crosstalk simultaneous switching noise for improving signal integrity in SOC-based processes. His whole journey teaches us new learnings and a great platform to gain more knowledge. Adding to it, he has attended more trainings, FDPs, and got certified in various courses too. His motivation and multitasking abilities will made us to keep learning more from him. We hope that his teaching experience, optimistic approach, and skillful mind together will help us to build good knowledge. Last but not the least, I would welcome all the faculties on this occasion. Once again, I welcome you all. Now I hand over the session to the resource person.
Thank you, sir. Welcome, sir.
So thank you. Thank you, madam. Thank you very much for your introduction. Good morning. Good morning to everyone. Sir, my voice and video is clear, sir?
Sir, clear, sir, but noise produced, sir.
Now, okay, sir?
Yeah, clear, clear. Good, sir.
Okay. Actually, fan is running. I switched off the fan. Now it will be better. Okay. So now, can I share the PPT, sir?
Sure, sure. Okay, sir. Okay, sir. Continue, sir.
Okay. Okay.
Sir, visible, sir?
Visible, sir? Okay, okay.
Yes, yes. Okay, sir.
Okay, good morning to one and all present here. First of all, I express my sincere gratitude for the head of the Department of EEE and the coordinators of this FTP program for arranging AICTE sponsored FTP on the topic of applications of machine learning and deep learning. Because of everybody is in pandemic situations, we need to update our knowledge in online mode. So in this aspect, you have developed this AICTE sponsored course. Actually, it is a very good initiative taken by your department. Okay. Now, before getting into the subject or the topic, digital image processing. Actually, all the images used in this PPTs are taken from the original source, like a medical image or any satellite image. Actually, at the references, I included the references also, but it is prepared only for the academic purpose. So this is the basic outline of our session. It starts with introduction about DIP, digital image processing, then fundamental steps involved in digital image processing. Then the third topic is image enhancement. In the fundamental steps of digital image processing, we have different steps, different methodologies. So among the different methodologies, image enhancement is very important. So we will see image enhancement, then image compression. That is also one type of image processing algorithm we are using in the image processing to reduce the bandwidth of the image for the better processing. Then image segmentation. Image segmentation is also an important digital image processing. Then finally we will see conclusion. Actually, in the fundamental steps, we have totally 10 or 11 steps. So covering all the 11 topics is difficult in this session. So out of different methodologies or steps, we have taken the important steps or the methods starting from enhancement, compression, and segmentation. So before we see the digital image processing, then the introduction, we will see the basic area related with the digital image processing. So these are the four different areas in which the digital image processing will take into part directly or indirectly. So whenever we are saying that processing means it is a processor or system, we have to give some input to the system. Based on the processing, we will get the outputs. So this is the basic image processing or signal processing concept. We must have a system, the processor, or simply we can say that processor. The processor will receive the input and it will produce the output. That is called signal processing. So in digital image processing also we have a system or processor at the center. It will receive the input, then it will produce the output accordingly. Okay. So if the input and outputs are images, both are images, then that area is our digital image processing. We are giving the image as the input and we will get the image as the output. So what is the process performed by the system? It will do some noise removal. Suppose some noise is present in the image, then we can remove the noise. So the output will be more pleasant than the input. Means that the output is the filtered image or enhanced image. Right? So in digital image processing, both the input and output are digital. Input and output are image. We will say digital image data, it is image, right? Then if the input of the system is image, then output is description. Instead of image, if we have descriptions, description means the output will contain some attributes of the image. Suppose if we are showing on image, on family image, father and mother and the two kids image, family photo. Then in human vision, we can say what is the image? We can say that it is a family of the image. Sorry, it is the image of the family consisting of 4 members, right? In particular, if we ask the question, we can say the color of individual persons, background or the area. So that is the attributes or the specifications mentioned by the human vision, normal human vision. Suppose if we ask about the resolution, what is the resolution of the image photo? It is not possible. What is the intensity? What is the compression? Compressed. What is the space of the storage capacity of this photo? It is not possible by the human vision. So these attributes are expressed by the computer vision. So the input we are giving image only. So based on the computer vision, it will give some attributes about that image. In that image, we will have the informations other than our human vision, normal human vision. So that area is called computer vision. Input is image, output is descriptions. No image. And the third category is reverse. The input is descriptions about the image. Output, we will get the image. Input is only attributes. Output is image. That field is called computer graphics. Normal computer graphics, CG. If you want to draw one circle, then we can give some specifications or the parameters, like what is the origin of the circle, then radius of the circle, we have to give as the input descriptions. Output, we can generate the image of the circle. Right? The origin is known, then the radius of the circle is also known. So we can generate the circle. That is, output is image. That is computer graphics, CG. Then finally, artificial intelligence. So in this category, both input and the outputs are descriptions only. We are specifying the inputs, parameter or attributes about the a particular image. Then it will produce descriptions only. So what is the difference? Input is description, output is description. What is the function of this artificial intelligence? It will apply some intelligence. Suppose if it gives partial information, partial description about one particular object as the input, then the artificial intelligence will identify the output, which is up to more than 90% or 100%. Ideally, we are saying that by having the 50% information, the artificial intelligence will develop the 100% output. So by having partial information, we will generate the entire image or output. That is also in descriptions. So in artificial intelligence, now we are using this machine learning and deep learning. So that is the your topic of your FTP. What are the applications of machine learning and deep learning with respect to the electrical engineering aspect? So in the artificial intelligence, both input and outputs are description only attributes, no images. So out of these four, we will see the first two, digital image processing, that is both input and outputs are images. Then we will see about the second one, computer vision, that is input is image, output is descriptions. CG and artificial intelligence we will not cover here. Our objective is image processing. So in all the cases, image processing will be played an important role, whether directly or indirectly. Got it? So if we put a simple question to the baby or kid, what is the image of elephant? So if the question is asked to the adult, then it is easy. For a small baby, if we ask one simple question, elephant, for that we are giving some descriptions about the image. The elephant is black in color. We are giving some specifications about the elephant. It is gigantic in figure. It has 4 legs, a trunk and tusk. If we are giving the specifications like this, then the baby cannot understand what is the expected image output. With respect to her imagination, it is difficult. Right? So instead of giving this much of description, if we show this image, then the baby or the kid can understand the image of elephant. So what is the objective of showing these images? One image visual representation is very effective too, rather than descriptions about the object. So if we show the image visually, then it is easy to understand the complete image by anyone, not only with respect to the baby, for adult also. Right? So visual information is more powerful than textual information. So in general, in digital image processing, to enhance the importance of image, the second point is given. One picture is worth more than 1,000 words. Even in the previous example, we can give some additional information also about the telephone. We can give, for the example, we have given 4 descriptions. We can give some more attributes also. But even if we have more information in...
Sir?
Yes?
Sir,
Yes,
the
madam.
slide is not actually changing, sir. Fundamentals of digital image processing. Are you changing the slide? We could not see the slide changing, sir.
Oh, wait.
Thank you, sir.
How it is changing, madam?
No, sir. It is in the first slide. It's in the first slide, actually. That is fundamentals of digital image processing. That slide it is.
This fundamental slide is visible, madam?
Yes, sir.
Sir, slide number one is selected, sir.
Okay, what about slide 2? Slide 2 is visible, sir?
Screen is visible, sir, but the slide is the same slide remaining. There is no movement.
Now I am changing the slide. I can see. Can I reload the PPT once again, sir?
Sir,
Okay,
can
sir.
you
Okay.
put it in the presentation mode, sir? I think F5 you can press.
F5.
Sir, once again your share slides, sir.
Once again, if you share, I think that will be okay, sir.
Wait.
Yeah, yes, correct, sir.
Now the slide is visible, sir?
Yes, sir.
Next slide, sir.
No,
Once
but
again, the
you
fundamentals of digital image
right side
processing.
only for first slide are selected, sir. So the first one slide is here visible.
Okay.
What
What about the slide, sir?
F5.
Sir, if you move the page down, maybe it is. Yes, now it's slide share, sir.
Oh, okay, madam. Now the slides are visible?
Slide visible, sir, but empty slide visible.
Empty slide.
Yes, sir. It is an empty slide. Just shift to the next page. Slide to the next page, maybe, sir.
Oh, okay, madam. Second, third.
No, sir. It is a plain slide. There is nothing displayed on that. It is a plain background screen
If
of
you
your slide.
take for few minutes, sir.
Yes, sir. From my side, it is changing. Then what is the problem?
Minutes for the network issue, sir. So no problem.
How is it okay? Oh. I reloaded that PPT again, then again.
Actually, there is a slide with the first
Wait.
slide alone is showing, sir.
the right side of the screen, here zoom and change the value nearby the one computer symbol. Just click the computer symbol, change the mode of the presentation mode, sir.
Sir, I will try once again, sir.
Okay, sir. Okay, sir. Screen is visible, sir.
Wait, sir. Wait, sir.
The screen is the right at bottom, sir. The zoom option available. Nearby the one computer icon.
At the bottom, it shows, sir, actually, it is showing stop sharing, hide, and that information it is showing at the bottom.
Okay, okay, sir. About screen slate, sir. Just to change the slate, sir. Okay, sir. Visible, sir. Change.
Yes, sir. Yes,
Yeah.
sir. It's coming correctly. Sir.
Now, okay, sir?
Yes. Yes.
Okay, sir. Fine, sir. Fine.
Okay, okay, sir.
Thank you.
Thank you.
Sorry. Thank you, madam. Sorry for the inconvenience occurred.
No problem.
We will proceed. Again, I start with this basic category. In the first category, both input and outputs are images. Then the area or the process is called digital image processing. If the input is image and the output is the descriptions, then it is said to be a computer vision area. It is a different area. The processor will receive the image as the input, and it will produce the descriptions, that is attributes about the object or the image. The image attributes will be getting at the output, that is descriptions. Right? And the third category is the input. We are giving that description about the image. Based on that, it will produce the image. That area is called the computer graphics. We can draw any diagram. For that, we need to specify the descriptions. Some specifications or attributes about the image we have to give as the input. So input is the descriptions, output is the image. That area is computer graphics. And the last one is input and outputs are descriptions only, no images. Only we are giving some inputs in terms of descriptions. Based on the function of artificial intelligence process, we will produce the descriptions. So in this area only we are applying that machine learning and deep learning for any specific applications we are using. Now in this session we are going to see about the first area called digital image processing. That is the first quadrant in which both input and outputs are images. Then we will see the computer vision also. That is, input is image, output is the descriptions. Then bottom, computer graphics and artificial intelligence we will not cover. So our objective is the digital image processing. What are the fundamentals, steps or the fundamental concepts used in image processing we are going to see. I think it is not necessary to explain this example once again. In order to mention the importance of visual information, we are giving this example. So no need to give the description about the image. So the number of descriptions, it is our choice. It is not restricted with 4 or 5. We can give any number of description or attributes about the image. But instead of giving so much of textual information, so just if we show the image, then one can easily understand what is the image exactly. So one picture is worth more than 10,000 words. We can give any textual information, any number, but if we show a simple picture, then we can understand clearly. So that it describes about the importance of image. So now we see about the digital image processing. So before we see the digital image processing, let us see what is image. Normally it is coming from signal. I think you may familiar about the digital signal processing, DSP, in which the signal will be defined with respect to one-dimensional function. One-dimensional function. It possesses some information. It possesses or it contains some useful information. If you talk about with respect to electrical engineering, one power signal, a single phase power signal can be represented by a signal which is having one-dimensional, x of t equal to a sin omega t. It is a sinusoidal signal. Okay. So the independent variable or the function of the variable is t, x of t or y of t. So it is a signal. Simply we can call it as a signal. If the function contains two variables, then it is called two-dimensional signal, 2D signal. Okay. Like that, we can have a multi-dimensional signal, 3D, 4D, any dimension we can. So it is coming from the word signal alone, 1D signal, 2D signal. So the image is also called as a 2D signal. So in technically we are saying that the two-dimensional signal is the image. So it is a two-dimensional function. The dimensional variable is expressed by the spatial coordinates, say x comma y, and the value of f, the function, will have the intensity of the pixel at that point. Mathematically, it is like a point. A point is expressed by two coordinates. The image, the consisting of so many points, that is called as pixel or picture element. So at each pixel, the function f must have some intensity of that particular image. That is called a two-dimensional function, or simply image or 2D signal. Actually, we are doing a digital image only. The input is a digital. We are discretizing the image into digital. So which image is called digital images? We have a two-dimensional function in the image, that is the spatial coordinates x comma y, temporal coordinates. These spatial coordinates x and y and the function f, that is the intensity of the pixel, all are finite and discrete quantities. It is a finite and a discrete, individual. Instead of continuous, we are taking into a discrete. Then the image is called digital image. Both x comma y spatial coordinates as well as the function f value, intensity, must be represented in discrete. Such image is called a digital image. Now we see the third process, or the third important point, called image processing. Image processing or digital image processing. So digital image processing, we are going to process the digital image in digital computer. We are giving some input, digital input, to that computer or processor. Then it will produce the output. In the first slide, I have given that one. Input and outputs are images, right? The image is a digital image. So it will do the process in digital sense. That is the meaning of digital image processing. It contains several methodologies or the steps. One is image transform, then image enhancement, image compression, image restoration and reconstruction, then image segmentations. So these are the important image processing used in the so many areas, not only in electronics or computer science. It will be used in electrical side also. Image transformation. Just we apply some transformation like a Fourier transform, then the image will be transformed in frequency domain. Image enhancement means the quality of the image will be improved in some sense. Okay? That is the image enhancement. Then image compression, if we want to minimize the storage capacity of the image, then we can go for the image processing algorithm. Then image restoration and reconstructions. Once the image is degraded in the degraded function, known function, or addition of some noises, then we have to reconstruct the original image. That process is called image restoration. Then finally, we will see image segmentation. Image segmentation means at the input we are giving the digital image. We will do some partitioning. The whole image is separated or partitioned into individual sub-images. Then we will do some process. It will be useful in finding the tumor or stone detection in biomedical engineering. Or instead, general application is boundary detection. Edge detections, we can use this image segmentation. So, as I said earlier, the 2D function is called as image. So it is given in both dimensions. Dimension 1 as x-axis, dimension 2 is y-axis. So in 2D image, we have more number of pixels, picture element. F of x comma y is the one specific pixel. If we take x equal to 0, y equal to 0, then we can find out the pixel at origin. Both x and y coordinates are 0, 0. So at origin, what is the intensity, gray level of the image? Then if we give x coordinate is 1, y coordinate is 0, 1 comma 0. That is also one pixel. Since it is a discrete, we are specifying only the integer values. X and y takes only integer 0, 0, 0, 1, 1, 0, 1, 1, 1, 2, and so on. So it is specified in terms of matrix. So rows and columns we can specify. Similarly, the same 2D image will be represented in 3-dimensional also, 3D image also. So it has one more dimensions, dimension 3. It is one simple grayscale image. It is represented in matrix, rows and columns. So it contains several rows, which is expressed in a horizontal line, and the columns in vertical lines. The junction point of each rows and column is our pixel. So even we can give more number of rows, more number of columns, we have more number of pixels. Right? So if you want to find out the intensity of the particular pixel, then we can find out the gray level. What is the gray level, or what is the intensity of the particular pixel? I will show what is the gray level or intensity in the successive slide. So these are the different areas in which digital image processing will find its applications. More applications are there. Just I have listed only a few of them. In the entertainment side, we can capture the image of natural sceneries, or we can capture the image of sports. Then we will find out that quality, then we will do some process. Then in medical area, it will be playing a very important role in the diagnostic side for finding the different images like X-ray, MRI scan, CT scan image. You can apply this image processing. Then third category is remote sensing, which will be used for satellite image picture, or we can capture the picture in a remote site using the radar. So it is a satellite picture or radar picture. If we want to find out the weather report, then we can get the picture from satellite so that we can predict the satellite. That is, we can predict the weather. Then it will be used in forensic field also, investigation side, in particularly in police department, fingerprint scanning, then iris, so many parameters we can apply this image processing in the investigation purpose, particularly in forensic field. So for the introduction, some of the image processing examples I have shown here. So it is the one type of image enhancement technique. On the left hand side, we have one image which is low contrast image. The contrast is very, very low. Contrast means actually we have two terms we are collectively using. One is the brightness. Brightness is the complete brightness or complete darkness. That is called our brightness. But contrast is, it is the difference in brightness with respect to object and the region. Region means boundary. If a boundary and the other region and the particular, yes sir, object, if both are in the same brightness, then it is difficult to visualize the image. So that is the case showing in the left hand side. All the images and the boundaries are very, very bright. So in order to do better processing, then we are doing that enhancement technique. That is that process is called contrast stretching. Contrast stretching, so that the right hand side is more present than the left hand side image. So it is a contrast stretching methodology, particularly used in the image enhancement. Another image processing example is the image enhancement technique. Here also the internal nerves, it is the image of eye. The nerves inside the eyeballs are not clearly visualized in the left hand side. So in the after performing image enhancement, we will see the nerves and the background clearly. So this is also one kind of image enhancement technique. We will see in detail what is image enhancement, segmentation and compression in the successive slide. Just for intro, I am giving some examples with respect to the image so that you will have some idea. So this is another image processing example. In the left hand side, we have a blurred image. The image is not clear because of the different parameter. If the focusing of the camera misfocused, then we will get this blurred image due to the misfocus. During the focus, capturing that image, if we shake the camera, then we will have this image like that, blurred image. So de-blurring is one image processing technique in which the blurred image will be visualized clearly. So during the motion, if we are moving in a vehicle or car or bus, if we are using our mobile phone, if we shoot one image, then it may be clear or may not be clear because of movement of the camera. The image is in blurring. So it will be looking like left hand side image. So in order to see the image clearly, we are doing some de-blurring algorithm, that is image processing, so that the image will be more pleasant than the previous one. This is another example showing that image restoration. This is image restoration, in which the left hand side image consisting of some dots, that is technically it is called as salt and pepper noise. The black dots and white dots will be there. So removal of salt and pepper noise will give a pleasant output. So this is one technique coming under image restoration. We can reconstruct the original image in the degraded scenario. So this is another example showing that segmentation. So left hand side is the original image showing the entire part of our hand. The right hand side we are doing some segmentation technique, image segmentation. So the segmented image will showing only the boundary of our hand, not the internal structure of our hand. The internal structure of the hand is not visualized clearly. Our objective is to detect the boundary or edges of the finger as well as that bolt. We are applying that image processing, particularly segmentation. So this is the segmented out. The same image will be processed with respect to the internal texture also. If this is the external property, image segmentation will be processed in two ways. One is external property, we can apply the segmentation. Internal properties of the image also we can apply. What about the color of the pixel? What is the pixel size? Then what is the texture? Everything we can apply in terms of image segmentation also. That is tumor detection, brain tumor detection. Only the tumor is present inside the brain. So if you apply the image partition technique, then the location of the tumor as well as the size of the boundary is known. Once the boundary is known, then we can find out the dimension, what is the size of the tumor, or whatever we can call kidney stone detection. We can apply this segmentation algorithm. That boundary information. So in the beginning slide, I have shown about the computer vision. And the input we are giving that image, output it will be a description about that image. So it is the boundary of one particular animal. So without mentioning any other information about the color, and the yes, sir? We can easily find out the name of this animal, giraffe. So only the boundary is available. So based on the boundary, we can find out this is it is decoded as a giraffe. So in that case, only the boundary information is sufficient. It is not necessary to specify all the internal explanations of the internal structure, color, and other things. Not necessary. So this is also one kind of image processing technique, which is obtained at the output of segmentation. So these are some examples related with image processing, namely enhancement, then image restoration, segmentation. So we are familiar with how the image is formed or visualized by the eye by means of two processes. One is incident of light over the object and the reflection of light from the object. Two processes. That is called illumination. This is the light source from the sunlight, which is incident on the object, and it will be reflected back. So incident and the reflections. Two processes it is performing. Once it is reflected back, our eye will receive that image. So sun is the source of illumination. Okay. So based on the incident of light and reflection of light, we are seeing that image. It is a simple science already we are familiar in school level. Again, it is given in terms of a two-dimensional diagram. Point source of illumination obviously from sunlight or any source of light. During the daytime, the source of illumination is obviously from sun. During the night time, any other sources, light or LED sources. So by exposing that object over the by exposing the light over the object, then we can visualize the image by reflections of light from the object. So this is a basic idea how the image is formed or how the image is visualized by the human eye. It is one standard electromagnetic spectrum in which different regions are classified with respect to its frequency or wavelength. Wavelength and frequencies are inversely proportional. So in the left hand side we have the gamma rays, after that X-rays, UV, then human visible region, that is a light, then IR, infrared, microwaves, and then FM radio. On the left hand side, the gamma rays will have the highest energy as well as frequency. 10 power minus 12 is the wavelength. If you take the inverse, then it will be given in terms of frequency. So it is a very, very high frequency and high energy signal. Then X-ray is somewhat smaller than the gamma rays in frequencies as well as energy. Like that, ultraviolet is smaller than X-rays and gamma with respect to frequency and energy. After the UV rays, we have our visible light sources by the human eye, starting from 400 nanometer to 700 nanometer. Only in this region only our human eye will see that object, starting from violet to red. Then after that IR, infrared, microwaves, and FM radio. So we will see each one example for each category. Gamma ray will be very much useful in nuclear medicine as well as astronomical observations. So in nuclear medicine, we can inject a patient with a radioactive isotropic traces that emits the gamma rays. This is the source of gamma ray. So once it is injected, then it emits the gamma rays, which has a high energy as well as high frequency. So it will be useful in the nuclear medicines to study about the bone pathology or to find out the infection or presence of tumor, everything. We can go for gamma rays. It has a high radiations with respect to energy as well as frequency, very, very high. The same gamma ray will be useful in the astronomical study also. So in the space study observations, we can take this astronomical observations, particularly by the gamma ray. So this is one example showing that gamma ray images of a human body in which the entire bone structure is clearly visible. Once any abnormalities are present with respect to the fracture or with respect to study about the disease, even if we want to find out any fracture with respect to the bone, just we can go with the X-ray. In that case, gamma ray images is not necessary in biomedical applications. But in order to study the analyze the bone pathology or any detection or any detection about the tumor, then we can go for this gamma ray image, which has a high frequency and a high energy. Obviously, we are familiar with the X-ray. It is the next category in the electromagnetic spectrum, which has smaller with respect to gamma ray in frequency as well as energy, in which we can use this X-ray images for diagnostic purpose. So an ultraviolet will be useful in finding the microscopic study, in which we can find out the images using this UV radiations or UV light, like lasers or biological imaging, or even any astronomical images. Also, we can use this UV light. So these are some typical examples of ultraviolet light used in the fluorescence microscope. Even if you want to find out any virus, like coronavirus or any typical virus, we can go for this microscopic imaging by ultraviolet. Then the next spectrum is our human visible region. That is our visible regions starting from 400 nanometer to 700 nanometer, in which we can see the image by the human eye clearly. An IR image is looking like that. With respect to the visible light of the human, it is slightly varying, but the clear image is not visible by using the infrared IR and the radiations. And finally, we have a microwave and the radio wave electromagnetic spectrum, which is very, very minimum low with respect to frequency as well as energy when comparing with the gamma rays and the other X-rays. So it will be used in the radar, particularly in the remote sensing image capturing using the radar. We can go with the microwave band. Then again, radio wave is the last electromagnetic spectrum range. Here we can use this radio wave for communication as well as medical as well as astronomy purposes. So this is one image captured with respect to the radar. Mountains of southeast Tibet. It is taken from the NASA. So even in a worst climate, lighting or a bad weather conditions, the image will be captured clearly. That is the concept of a microwave band. So in that case, the light facility and the weather condition is not up to that satisfactory level. It is very, very dull. So during these worst situations, we can visualize that image captured by the radar using the microwave band. And finally, radiologists. Radio waves, particularly, it will be useful in the MRI scan imaging, magnetic resonance imaging. We are using this radio wave band, but again, it will be given in the medical applications only. So this is the overall image about one graph pulsar image, which is one star, young star image, which is captured using different radiations by gamma ray and X-ray, optical, that is a light source, then infrared, then finally radio. We can see the differences. So depends upon our applications or requirements, we can select any one of the radiations, either gamma ray or X-ray. As I said earlier, the same X-ray will give the bone structure also when compared with the gamma. So, but the limitations will be very, very narrow in case of X-ray. So in that case, we can go for the gamma rays. Like that, one single image will be visualized. The different rays are given here. And this is one image called SAR image, synthetic aperture radar image. It is an aerial image captured by the radar. By using any other radiations or rays, it is difficult to find out this overall visual aerial visibility. It is difficult. So this is a synthetic aperture radar, which is used in the remote sensing applications. The biggest area will be visualized. That is the particular specific area. It is difficult, but the overall area about the particular region or particular sector can be visualized using this SAR image. Then now we will see the difference between RGB, that is a color image, grayscale image, and black and white image. Color image, already we are familiar. It is a true color image, red, green, blue. It is called primary color. So each color will use a grayscale range between 0 to 255. That is a grayscale. The meaning of grayscale is each pixel is represented by 8 bits normally. Each pixel, one image consisting of several pixels, each pixels will be represented by 8 bits. So 8 bits means the range of grayscale will be calculated by 2 power 8. 2 power n formula. Number of bits used into pixel is 8. So 2 power 8 is 256. So 256 is the range of number of gray levels present in the grayscale image. Usually it is varying between 0 to 255. That is the second one, grayscale image. The pure block is represented by 0. Pure white will be represented by 255. So 0 to 255. Why we are getting 0 to 255? It is a grayscale range of an image since it has totally 256 gray levels, 2 power 8. So leftmost is the 0 that is assigned with the black color, and the rightmost is the 255 which is assigned with the white color. In between we have variations with respect to black to white. So that is called grayscale. Got it? The third image is our black and white image. It is purely white and black, 0 and 1 only. There is no other range like a grayscale. But based on this grayscale range only, we can generate this RGB color, red color, green color, blue color. All these three primary colors will use the individual grayscale array, in which the grayscale will be varying between 0 to 255. So 0 to 255 grayscale will be assigned to red color. That is the first channel for RGB. Then again 0 to 255 grayscale is assigned to green color. That is the second channel. Then third channel, that is the blue color, is again assigned with 0 to 255 grayscale, so that by using the grayscale we can generate the entire true color using RGB. So black and white image is simply a binary image. So the image of the parrot is it contains only white and black. That's all. There is no other colors like a middle grayscale. Since it has a grayscale range starting from black, then after that dull black, then again dull black. Black is gradually decreasing if we increase the grayscale level. At final, we are getting the pure white color if the grayscale level is 255. Then another one is the type of file type. In which file type we are storing that image. That is, with respect to the file type, it is classified into raster and a vector image. The left-hand side image is a raster image. The raster image means the file is stored with respect to the pixel-based software. Normal pixel-based software, we can store the file type like a JPEG file, PNG file. These are comes under raster. So in raster, if you look into the top circle, which is scaled with a 3:1 ratio, if we zoom the particular portion in a cycle, the zooming level, the zooming dimension is 24:1, so that we will see the smaller tiny particles. The pixel will be zoomed, so the original image will be changed if is scaling. So first one is a 3:1 scale in a raster. If we zoom in, then the image showing with respect to particular portion means in the circle will contain small tiny pixels. So the image is not clear. So the quality of the image will be changed. That is the raster type image. Vector image means even the image will be scaled down or scaled up with respect to 3:1 or 24:1. Even if we perform the zooming, the image pixel will not be changed like a raster image. Okay. So that type of vector image file is represented by vector image. Example, we can use this image in the 3D animation, and particularly in a CAD design. If we draw a CAD diagram for civil engineering purpose, one plan of the building, then even we can increase the scale or decrease the scale, the image will not be degraded. So in that case, we can use that vector image, not a raster image. If we use a raster image, if we expand that scaling or if we zoom in, then the quality will be reduced. We cannot see that a particular image pixel clearly. Right. So whenever we are expecting the quality in the scale up and the scale down, we can store the image in vector image format only. Right, CAD design, 3D graphics design we can use. The file type will be .svg, scalable vector graphics. So that is a file type. Several file types are used. .ai, then other formats are used in the vector image. .svg is a familiar. This is again another example showing the raster and vector image. Left hand side is a raster image. It is a pixel based image. If you zoom in, then the pixel quality will be changed. Right hand side is the vector image. So it shows the scaling, scale up or scale down, the quality will be same, not changed. So that is another example showing a raster and a vector image. With respect to the color image, we have to see the resolution. What is the resolution of the image? So in the left hand side uses the high resolution. Right, with respect to the number of pixels. Now we are saying that resolution in terms of HD or full HD, 4K, right? We are saying with respect to the resolutions in a smartphone or even a television, we are saying that HD quality or full HD quality. It is based on the number of pixels. If more number of pixels are used, then it has the highest resolution. The right hand side image is color image of the flower having less resolutions. The number of pixels are minimum when compared with the first one, so that we can see the differences. But anyhow, if we increase the resolution, proportionally the storage capacity also increases. So that is a drawback. Quality aspect, it is good, but with respect to the storage aspect, it is not good for high resolution image. This is the different gray scale images with respect to 8 level, 32 level, 64 level. As I said earlier, each pixel in the image will be represented by 8 bits. So totally we have 256 gray levels. So it is starting from 0 to 255. So if you look into the 8 steps in gray level, the leftmost band is a black color, that is a 0. Right side is pure white, that is 7, 0 to 7 is the grayscale range for 8-step gray level. At the middle, we have variations. Gradually, the black color is degraded, and finally, it will be pure white. 0 to 7 is the grayscale range for 8-step. Similarly, 32 step means 0 to 31. So, like that, we can express. If more number of gray levels are used, then more will be the clarity. If you see an example for different gray level resolution. Yes, sir. My voice is clear? So can we proceed?
Yes, sir. Okay.
No, yes, okay, sir. Okay. So in the topmost image is the original image. Right top corner we have the image with the 64 gray levels. The same image will be shown by a 16 number of gray levels, 0 to 15. Then finally 8 gray levels. The same image is shown. If we see the 4 diagrams, then we can understand the importance of number of gray levels. So if low will be the gray levels, then low will be the resolutions. The quality is minimum. Even if we increase the number of gray levels more than 64, like 128 or 256, then we will find out the clear grayscale image. Normally, as I said earlier, the image is represented in matrix format, rows and columns. So this is the way of representing images in a matrix format, digital image representation. starting from 0 to n minus 1. So we have n number of columns, 0 to n minus 1, m number of rows. So in that case, we have m by n number of pixels. If we take one pixel, which is mentioned in terms of its coordinates, x coordinate and y coordinates. So if we represent in matrix format, f of x comma y, f of 0, 0 is 1 pixel. Origin, 0th row, 0th column, we have 1 pixel, 0, 0. That is the location of the pixel. The intensity or the gray level of the pixel will be defined by the function f. That is the meaning. Then f of 0, comma 1 is another second pixel with the second column. That is the first column with 0th row. Like that, we can represent the entire pixels in terms of rows and columns matrix. So the picture element, the position of the pixel will be represented or provided by the spatial coordinates x and y.
I'm not getting the pictures. PPT is not visible, please.
How, sir?
I'm unable to see the PPT. Now yes, yes, now it is. Okay, okay.
Now visible, sir?
Yes,
Yes,
sir.
yes. Yes.
Okay. So the same image will be represented in terms of matrix by its different spatial coordinates x and y, so that the image will be represented in matrix as well as it is represented in digital. As I said earlier, both x and y x and y values as well as the f of x comma y will have a finite and discrete quantities. Here x and y are discrete, 0, 1, 2, 3. Similarly, the individual pixel having the amplitude or the intensity of is also discrete, so that this image is a digital image. So normally, with respect to the previous slide, the image will be represented by number of rows, which is mentioned as m, and the number of columns n, the number of gray levels. So if we want to represent the digital image for a grayscale image, then the third parameter is very important. What are the number of gray levels we used? Normally, the formula for gray level L equal to 2 power n or 2 power k is varying between 0 to L minus 1. Since the gray level images are represented, each pixels are represented by 8 bits, so 2 power 8 totally, we have 256 gray levels starting from 0 to L minus 1, so 0 to 255. Then finally, B is the number of bits required to store a digital image. Here, K is the number of bits. With respect to the gray levels, if we are using the gray levels 8, then 2 power 3. 3 is the number of bits required to store the image. Okay? If we are using a 64 levels of gray levels, 64 different levels used in the gray levels, and 2 power 4, 64, sorry, 2 power 6. 2 power 6 is 64, so 6 bits are used to store that image. So here B value is 6. Like that, we can find out the B. B is the number of bits required to store a digital image, which is obtained from the gray levels only, from the above formula, L equal to 2 power k. So if you assume as a symmetric matrix in which the rows and columns are equal, m and n are equal, so that the bits B is equal to n, m into n are same, so n square into k. That is the size of the image for finding that storage capacity. So this is a table showing a different n by k value. What is the size? The first one is 32. N value is 32. Here n and m are same. So 32 means 32 into 32. N squared into k is the formula for finding the storage bits. If you want to represent one pixel, what is the storage capacity? Okay. So for that, the entire bits are calculated. If we consider different gray levels, starting from 2, 4, if gray levels are 2 means 2 power 1, 2 power 1. So number of bits used to represent the gray level is 1. So what is the size of that image for 32? 32 into 32 into 1. So that it will be 1024. That is a storage bits required to store that image. Okay. Similarly, if we use the number of gray levels is 4. So the number of bits are 2 power 2. So n into n, again 32 into 32 into 2. 2048 is the pixel size. So like that, we can calculate the entire tables. Okay. Formula is n squared into k. Number of rows and the number of columns are 32. 32 by 32 into the number of bits used to represent the image pixel. That is, so at the bottom last row, it contains the maximum bits. For the number of rows, 4096. The column is also 4096. So 4096 into 4096 into the number of bits are 8 in the last one. I am saying the last row, last column. The calculations I am explaining. So 4096 into 4096 into 8. Number of bits is 8 for the gray levels 256. So we have this much of storage capacity. So once if you want to find out the storage capacity, then this calculations is very important. How many bits are used to store the represent the image? So from this, we have to select the number of gray levels. So with this, we conclude the first topic, that is the introduction. Introduction about the digital image processing. We have listed several examples of images, image file types, then enhancement in segmentation, then different applications of image processing. Then with respect to the image spectrum, how the images are formed with respect to different sources of light, we have discussed. Now we see the second topic, that is the fundamental steps in digital image processing. It is a generalized block diagram of digital image processing. So at the center we have the knowledge base. The knowledge about the individual image will be stored in this knowledge database, in a computer database. At the bottom we have the image acquisition. That is, it is starting with the image acquisition. Anything if you want to perform in image processing, first we have to capture the image. So getting the image is called the image acquisition. Then followed by several steps like image enhancement, image restoration, then color image processing, wavelet, multi-resolution processing, compression, image compression, then morphological processing. So up to morphological processing, we are at the first area, that is digital image processing. So in the introduction slide, I have mentioned if the input and outputs are images, then it is called digital image processing, right? So starting from the image acquisition to the morphological processing, outputs of these steps are generally image. So that is the first one. So we are dealing with the digital image processing. After the morphological process, it is represented in terms of segmentation, then representation and description, then finally object recognition. These outputs are not in image. It will be represented in terms of descriptions, right? So output of these steps are generally image attributes, descriptions. So it is related with the computer vision. Input is image, output is the attributes or the description. So it is given in terms of major area called computer vision. We see one by one. Image acquisition is the first process. So as I said earlier, the image will be captured using a camera. Normally, we are using the hardware device for processing this image acquisition. It will be a raw image, right? The image will contain any noise also because of the mishandling of the camera or the quality of the lens, then quality of the image camera. It will contain some noises or blurring. So that is, we will do some noise removal or called pre-processing. Before processing, the captured or acquired image will be undergone to a process called pre-processing, in which the basic noises will be eliminated or removed. So this is the first step in the image processing, image acquisition, getting the image, how we are acquiring the image. Normally this will be used by these hardware devices, right? So we can get, even if we get any quality of the camera, we will do some process called pre-processing to remove that noises. Then we will apply any one of the technique like enhancement technique or compression or segmentation. The second step in the image enhancement is image processing step is image enhancement. So it is the process of improving the quality of the image. It is the process of adjusting digital images so that the results are more suitable for display or further image analysis. As I said earlier, it is a raw image. After pre-processing, the basic noises are removed. But if any specific noise is present with respect to the brightness or contrast, we have to perform the enhancement, image enhancement. So the output of the enhancement, image enhancement, we are getting a pleasant image rather than the previous image. So which will be very, very good with respect to the quality by the human eye. So it is subjective in nature. Suppose that in the very introduction slide I have shown the first example, contrast stretching. The weight-based color gray level is a dominating color that will be enhanced by means of contrast stretching so that the individual objects are seen clearly. So this will differ from person to person. Some persons will prefer that low contrast image. Some persons will prefer high contrast image. By seeing the image, television, we can know somebody will give the high contrast in the color settings. Somebody will set the contrast in low level or medium. So it will differ from person to person. So this kind of image enhancement is called subjective in nature. That is a point we specified in the second paragraph. In image enhancement, we generally try to modify the image so as to it more pleasing to the eyes. Anyhow, the output of the image should be more pleasant than the input. There is no doubt. But it is subjective in nature. So some persons will see the image in a low contrast or high contrast. So it will differ from person to person. So that's why it is called as subjective in nature. It is necessary, then we can do this enhancement technique. So normally enhancement technique will do some suitable display rather than the input. That is the concept. The third step is image restoration. Actually, it is the process of recovering an image that has been degraded by some knowledge of degraded function H. Actually, the image quality will be degraded because of some noises present in the surrounding environment, or even our processing equipments will introduce any heat or any noises. The image will be corrupted. So what we are going to do is we have to restore or reconstruct the original image with the knowledge of the degraded functions. We have to know. That is very important. So the knowledge of the degraded functions we must know. Then only we can reconstruct the original signal. But in case of image, this is also quality improvement only, right? But in case of image enhancement, there is no knowledge about the degraded function. By seeing the image, we can understand, okay, this is the contrast, so we have to improve the contrast, or we have to reduce the contrast, or we have to remove that noise. So in the first slide, I have shown another example, one baby image that is corrupted by the salt and pepper noise. This is the example. Removal of salt and pepper noise is only example of image restoration. It is not coming under image enhancement, it is image restoration. We know The degraded function is a salt and pepper line. So we can reconstruct the original signal by this image restoration algorithm. So it is objective in nature. So the image corrupted by the block and the pepper noise is not clearly visible for all the persons. For any person, it should be removed. Right? So it is objective in nature. That is the basic difference between image enhancement and image restoration. In both cases, the process, the output will be more suitable or pleasant than the input. There is no doubt. Then color image processing. So normally we are using a true color image, RGB image, red, green, blue images, or some another color models are used called CMY image, cyan, magenta, and yellow. That is a right hand side image is another color model specified by CMY. So in the RGB, in the color image processing, R color has the first one, that is in y-axis directions blue, Z is R, x-axis direction is green. So it is mentioned in terms of digital image. So 100, 100 is a red color image. It is mentioned in this order: R for red, green, second position. Black is blue is a third one. So 100 is the color positions of red. So in that case, green and blue are 00. Similarly, in the x-axis, it is a green color representation. So that its value will be red is 0. So first parameter is 0. Green is 1. So 1. Then again blue is 0. So 0, 1, 0 is this position of green color. Like that, blue color 0, 0, 1. It is a cubical representation. So here, as I said earlier, it will be each color will be represented with the gray level of 0 to 2.5. Right? So that grayscale is mentioned as the reflection of blue color as well as red color and green color. So at the bottom, in the inner cube, at the bottom, it is mentioned as black color. Opposite side is white color. So the dotted line indicates the grayscale, varying between black to gradually 1 with respect to the true color RGB color. Right? So in the second color model, it describes about the CMY color model, in which if we add the green color and the blue color, we will get cyan color. That is the topmost one, the first quadrant. We are seeing this one, cyan color, which is a combination of blue and red. Combination of blue and green. Green is the cyan color. Combination of blue and red is your magenta. Okay. Then combination of red and green is our yellow. So that model is abbreviated as CMY. That is mentioned in the right hand side. Just reverse to this one. So these are the two familiar models. In addition to that, we have one more model called HSI model, hue saturation intensity. That is also used for color image processing. Since the color image processing has 3 different colors for primary color, for each color we are using the gray levels 0 to 2.5. So the pixel number of pixels will be very high. That's why for color image we are using more pixels rather than grayscale or black and white image. In the next two processes, wavelets and multi-resolution processing. That is the next step. Wavelets are the small waveforms. Of limited duration, which are used to calculate wavelet transform, which provides time frequency transformation. So what is the use of this wavelet is, we can represent the image in terms of low compressed area. So if we use a wavelet signal, it is easy for compression. It is easy to compress, as well as it is easy to transmit also, since it has a finite or limited duration. This wavelet will be transmitted easily. The data transmission is very fast. So we are familiar with the Fourier transform. So the Fourier transform, the basis function is sinusoidal function, right? Normally the Fourier transform will be using sinusoidal transformations. So that basis function is a sinusoidal. But here the wavelet transformation is a small wavelet consisting of limited duration of high energy. So why it is used in multi-resolution processing? Multi-resolution means on a single object, one part will have one resolution. Another part will have the same resolution or different resolutions. If the entire object are having a same resolution, it is only one resolution. It is not coming under multi-resolution. So in that case, wavelet presence is not necessary. The entire image using only one resolution. But in case of multi-resolution, like a multi-signaling array, this wavelet is very, very important. Like a pyramid. Just imagine a pyramid-shaped image. Topmost one is a little bit portion. So in that case, we can represent the image with low resolution. Got it? So the multi-resolution is the one simple analogy showing the pyramidal image. Bottom is the large area, so in which the resolution will be high at the bottom. After that, it is gradually moving up. The resolution will be reduced because of the reduction in size. So with respect to the shape of the object, the resolution will be different. So that is meaning of a multi-resolution processing. It is not a same resolution. Depends upon the shape and the size, the resolution will be different. Smaller portion will have the minimum resolution. Larger shape will have a maximum resolution. So for processing such things, we are using these wavelets, small portions of the signal. Then compression, image compression is very important in image processing to minimize the storage capacity. Compression deals with the techniques for reducing the storage space required to save the image or bandwidth required to transmit. Not only for storage, even if we want to transmit, then it will be efficient if it is transmitted in a compressed form. Again, it will be based on the different category, Laplacian losses, we will see later. This is particularly useful in display images on the internet, as if the size of the image is large, then it uses more bandwidth or data to display the image from the server, and also it increases the loading speed of the website. Normally, if we are using image-based browsing in any browsers, if the images are represented without any compressed form, then it is difficult to process. Even displaying of one particular image, it will take more time. Even the processing, the loading speed is also very, very slow if we have an image without any compression. So in that case, the compressed images are very much used in the internet connectivity. In order to look, if we are working on a website which uses more images, definitely the compressed images will be loaded in the server. Then only we can download the image easily with less time. Then morphological processing is again the output of morphological process will contain only the attributes. Morphing means we can change the shape or the boundary of the image. It deals with extracting image components that are useful in representation and description of the shape. Suppose if we are detecting only image shape or boundary, then that length of the boundary, then what is the orientation of the boundary will be the attributes. That attributes will be extracted from the image components. So this extracted image components will be used in the morphological processing for changing. Normally, it includes two processes called erosion and dilation. So erosion is the one kind of morphological process in which the irrelevant shape, the irrelevant pixels used in the shape will be removed. The entire image will be shrinked, it will be compressed. And if wherever we have the thickness boundary, it will be thinned. The boundary thickness will be reduced, thinning. So the compression is performed so that the image will be shrinked, irrelevant informations are removed, the boundaries are thin. that process is called erosion. Dilation is just reverse. The entire image is expanded. So wherever we have the thin boundary, we have thicker boundary. Like that, we can increase or decrease the image with respect to the boundary or with respect to the pixels by using this morphological processing. And segmentation, as I said earlier, that it will be used for identifying any tumor or any stones present in a body, or finding the boundary of the image. If we are capturing an image, what is the dimension or what is the boundary of the image, then we can go for this segmentation. It is a process of partitioning a image, digital image, into multiple segments. We have to divide the image into sub images so that we can find out the boundaries or the internal texture of the image. Then representation and the description. So far, before segmentation, up to morphological processing, the input and outputs are images only. That is before morphological processing. After morphological processing onwards, the outputs of the processor are only attributes, right? Only descriptions. So representation is very important. Representation deals with converting the data into a suitable form for computer processing. We are not inputting any image to the computer. Okay? Just what are all the components we extracted from the image, it is represented by the attributes of the image. Then that attributes only feed it to the computer for processing. Such process is called representation. How we are representing the boundary or the region to the computer for processing. That is the meaning of representation. So this representation of a boundary will be represented boundary or region in terms of two ways. One is a boundary representation, that is the external shape of the characteristics. If we obtain one boundary, one image boundary, or even we used one animal image, giraffe image, that boundary is directed. Then how this boundary attributes are represented, that is it with respect to the internal characteristics. Right? We can represent the representation in terms of two methods. One is boundary representation, another one is regional representation. Boundary representation means we can represent in terms of external shape with respect to the corner or edges, we can specify. Regional representation means we can focus on the internal property. What is the pixel color, pixel size, then texture. That also we can give as attributes as a representation. So this how we are representing that segmented region to feed into the computer. That is the meaning of representation. Then description. How we are doing some representation in the previous process, right? How this representation is described. See, if it is a boundary, we are saying simply the representation is a boundary, right? If we take one example, the representation is a boundary of the image. How this boundary is described? How can we describe the boundary with respect to the length? What is the length of the boundary? We can give length is one important descriptor of the boundary. Then orientation of the line. What is the connectivity point? How in which directions the line or the boundary is moving? That is orientation. So orientation is another description. So in a single boundary, we can specify length is one of the descriptor. Then orientation of the boundary is another parameter or descriptor. Right? Then concavity, some curves, ups and downs will be there in the boundary. So that also we can represent. That is a concavity. So this length, then orientation, then concavity are the part of the representation. These are called description or descriptor. Ready? And finally, we have recognition. So it is the process that assigns a label. Example, car. It is given here. The object is car. to an object based on its description. So based on the description, we can identify the image or the object is animal, giraffe or car or whatever the image we have taken into our problem, we can recognize identification. So that part is the final part. So these are the important 10 steps used in the fundamentals, basics of digital image processing. Now we will see three important image processing, namely image enhancement, image segmentation, and image compression segmentations. So these are the three important areas. We cannot cover the entire image processing steps in 2 hours. It is not possible. So all these areas are individual chapters. So anyhow, we will try to the maximum extent. Image enhancement. In the image enhancement, we have to improve the quality of the image, which will be more suitable than the original image. That operation is called image enhancement, to process an image so that the result is more suitable than the original image for a specific applications. Or in other words, it is improving the quality of the image in some sense. So we don't know. So in some sense means whether we can increase the contrast or we can improve the quality, or we have to change the input in some sense. The process is called image enhancement. Right? So these are the types of different gray level transformations. We see one by one. Lazy main operation. The input is one image. At the center, it is the process performed by the processor or system. Output is the same image. Nothing will do. Whatever we are applying the input, the same image we obtain at the output. So the transformation is a linear transformation with respect to the gray level. If the gray level at the input on one pixel is 0, then the same pixel will be at the output is also 0. That is a linear variations with respect to u and v. Right? So this is a lazy main operation. So it will not do any improvement, but anyhow we can show this is that's why it is called as lazy main operation. No change. So the transformation is a linear transformation. Image negative, actually taking the negative of the image we are using, it is an inverse transformation of the previous one. So we have the negative slope with respect to u and v at the center. The transformation is inverse slope, inverse operation. So on the left hand side, wherever we have the black color, it will be visualized in white. Then white will become black. That is the image negative. Right? Here, even the output is not present with respect to this image negative, but it will be the input will be processed in some sense, so it will be useful for some applications. So like that we can extend applications of image negative. But in case of image restoration, the output is clarity output. There is no doubt. Right? The output will be visible clearly. That is image restoration. So this is image enhancement. So we are doing or improving the pixel quality in some sense. Another example showing the contrast stretching, what we use in the first introduction part. The transformation is defined with respect to 3 ranges. Linear transformation, it is not linear transformation. Up to some 3 levels, it is one transformation that is mentioned by the magenta color, A region. Between A to B, the transformation is changed. The variation of the x-axis pixel is not linear with the y-axis, YB. Then beyond B, again the transition will be changing. So what is the meaning is, between 0 to A, what are all the pixels present between 0 to A? A means some the pixel value, say 0 to 255, the pixel will be 70. 0 to 70, whatever the pixels present in the input image, the same pixel will be appearing in the output also. It is a linear. 0, left hand side is 0, output is also 0. That is the range specified in linear between 0 to A. A to B, it is changed. The gray levels are changed. X-axis is the input image pixels. Y-axis is the output image pixels. It will be changed. Again, beyond B, again it will be changed. So the output is somewhat different than the input image. So it is a contrast stretching comes under image enhancement. And clipping, just we can clip the image up to one intensity level, say 0 to A, that is mentioned in the red color. So here means suppose the intensity is 100, up to 0 to 100, whatever the output, it is 0. So in the input image, x-axis is the input pixel, 0 to 100, whatever the pixels present in this 0 to 100 range at the input, the output will be 0, black only. So between A to B, the pixels with respect to input image and outputs are changed with respect to the slope. Again, it is straight, it is clipped. So one portion will be clipped. We are assigning one portion of pixel gray levels are 0 or 1. That process is called clipping. And thresholding. Thresholding is similar to the clipping, but the thing is here we are not implying two different ranges. Right? Simply the transition is a straight line. So between 0 to 128 pixel levels at the input are assigned to 0 in the output image. Since it is at 0, here it is 0. So x-axis representing the input image grayscale. So it is the output is between whatever the pixels present in 0 to 128, it is 0, the output. Right? Even in the output in this range, the image pixels are 0 to 21, 20, 50, it will be assigned to 0. After 128, the gray level 128, it will be increased to 255. That is threshold. Here the threshold or reference is 128. That is the mid of the 256. Lower limit is 0, upper limit is 255. That is a grayscale range. If we fix the threshold at the reference is the midpoint, then the image will look like that. Another important term in image processing is histogram. So what is histogram means? It is a graph drawn between gray level of the pixel versus probability of occurrence of the pixel. The x-axis we are taking the gray level. Then y-axis, then we have to find out how many times that pixels is appearing. So in y-axis, the probability of occurrences of the pixels will be plotted. So that graph is called histogram. So the probability of occurrence is associated with the gray levels in the range of 0 to 255. So x-axis we have the gray levels range 0 to 255. Y-axis, how many times that gray level is appearing. That will be taken in the y-axis. This entire graph is called histogram. So for the example, here we have taken different gray levels mentioned in the matrix in the box left hand side. So this is 0 is one pixel gray level, 4 is another level. So here we are taking the 0 is the grayscale, 0. This 0 appears how many times in the image? We have to count. 0 appears here 1, 2, 3, 4, 5. So in the entire image, the gray level 0 appears 5 times. So we have to draw the graph like that, 5. Like that, all the remaining pixels are graphed in the y-axis. Right? Pixel 4 appears 3 times in the image. So we have to draw like that. We can draw the graph. This entire graph is called histogram. If you see the simple example, left hand side is the some low contrast image in which maximum white color is the dominating one. White. Anyhow, it is varying between 0 to 255 grayscale. There is no doubt. But majority of the pixels are having the gray levels closer to 1, 255. 255 means it will be closer to 255. 200, 200 or 195, something like that. So right hand side is the histogram graph. By looking into the histogram graph, we can see that between 0 to this is say 145 or 148. Up to this pixel, the number of pixels appearing is 0. It is more dominated, which is closer to the 0. It is dark color, that is black, which is moving far away from this one. They moving towards 255. It is the dominant of white color, right? So by seeing the histogram up to 148 or 145, it is a grayscale range. The y-axis is 0, means that no pixel is having that value. It is not occurred. The probability of occurrence of that particular pixel in this range is 0. That is the meaning. Between this range, here suppose say it is 150, for example, the grayscale 150 appears in the image more than 7,000 times. That is the meaning. You got it? So this is the graph. Exactly, if you take the pixel at 150, gray level 150, it appears in the y-axis number of times, right? 7,000. So it will be more dominating with respect to white. Again, like that, the pixel closer to the gray level scale 200, it is appearing maximum for 4,500 times. That is the graph. So up to 200, then 225, the pixel gray levels are appearing. After 225, no other pixel is appearing. That is the meaning of this histogram. So what is the meaning of this overexposed image? In overexposed image, most of the dominant grayscale are white, closer to 255, are varying between 148 to 225. It is overexposed image. So by seeing the image, we can say that this is overexposed. No need to see the image. By seeing the histogram, we can say that this is overexposed image. Let's see another example of underexposed image. Left hand side is it is dominated by black. So the histogram are closer to the 0. Here, the histogram is closer to 0. Between 0 to 50, maximum 50 grayscale, then it is appearing a number of times. After that, after the gray levels 50, it is 0. Means that up to 255, there is no white color. So it is underexposed. So by seeing the histogram, we can understand that it is underexposed image. It means that it contains the black color is a dominant color. Right? That is the importance of histogram. It is the example showing the histogram equalization, which is also one type of image enhancement. Top left corner is our original image, which is underexposed image, what we have seen in the previous slide. After histogram equalization, we are getting that top right corner image. That is this one. We can see the images clearly. So this is the corresponding original histogram, which is closer to 0. So it is dark. So what here we have performed is the histogram will be spread over the entire range 0 to 255, so that the image will be visualized clearly. In the right hand side bottom right corner, after histogram equalization, if you look into the histogram will be distributed between 0 to 255, so that we will see the image like this. Got it? So how it will be distributed? We have some algorithm. So we cannot randomly distribute the histogram. It will have some algorithm called thresholding. We can fix one threshold. Then after that we can move that, spread that histogram so that the image will look like that. Okay. So based on the histogram, we can do the image enhancement technique. Then another important technique in the image enhancement is spatial domain technique or frequency domain technique. As I said earlier, in the image, it has two coordinates, namely x and y coordinates. That is called spatial coordinates. So if we want to remove any signal, then we can go for the low pass filtering of the original image. It is called as one type of spatial filtering. We are doing the finding that we are replacing the original pixel value with its average of the neighborhood pixels. So that is the meaning of spatial low pass filtering, which is also coming under image enhancement. Let us see one simple example so that we can understand. This is the original image, 3x3 image. 7, 9, 11 are the pixels, grayscale value. Here we are going to change the grayscale of this original image. How we are changing? By finding that average of the neighborhood pixel. With respect to this pixel 7, this is one neighborhood pixel, this is another neighborhood, this is another. So with respect to the corner, there is no pixel above the 7, which is also a neighborhood pixel. Left to 7, this is also neighborhood. So by taking average of all the neighborhood pixels nearer to 7, that pixels will be replaced by the averaging of that value. Then the original pixel gray level 7 will be replaced by the average of the neighborhood pixel. You got it? Suppose in order to find out the neighborhood pixel, we can add the rows and columns by zero padding. This is the original image after zero padding. Input image after zero padding. Why we have to do? With respect to 50, we have the neighborhoods. This 9 is neighborhood, 5 is neighborhood, 6, 8, 10 are neighborhoods. But with respect to the edges in the left hand side or at the top, there is no neighborhood pixels. So just we are joining the zeros. That process is called zero padding. So here what we are going to do is this original pixel value is changed by average of these pixel values. With respect to 7, 1, 1, 2, 3, 4, 5, 6, 7. These are the neighborhoods pixels. 3, 3, 6, totally 8. 8 neighborhood pixels are there. Like that, this 9 will be changed. What is the neighborhood pixel for this one? This one, this one, this one, this one. Again 8. So in order to do this process, we are taking one mask having a 3x3 size, 3 rows and 3 columns with the weight value, some weight value. We are taking that gray level is 111, which is divisible by the average value. So totally 3, 3, totally 9 elements are there, each are having gray level 1. So the value will be divided by 1 by 9. So what is the meaning is, this pixel value will be average 1 by 9, this pixel value 1 by 9, this is 1 by 9. So we have to take one mask, 3x3 averaging mask with this size, having this average pixel grayscale value by 1 by 9. Then we can move this 3x3 mask over this image. Then we can find out the average of the neighborhood pixels. So in the next slide, this is the original image after zero padding. This 3x3 mask is placed over the original image such that the 3x3 elements will be covered. The mask is shown by the red color. The corresponding grayscale value will be mentioned as red color, 1 by 9, 1 by 9. Original pixel is 0 at the top one. This one 0, 0. So what we are going is this original pixel is multiplied with 1 by 9. So 0 into 1 by 9 at the bottom. The calculation is performed. 0 into 1 by 9 again is added with another neighborhood pixel. 0 into 1 by 9, then 0 into 1 by 9, 0. Here 7 into 1 by 9, that is 7 into 1 by 9. Then 9 into 1 by 9. Like that we can perform the average. The calculation is shown at the bottom. So that the new average pixel with respect to the neighborhood is 8.4. So this 8.4 will be updated in the original image. That is, this is the original pixel gray level 7. So the 7 is replaced with 8.4. Got it? So for this is our center pixel. This is our original pixel. This pixel will be modified by the average of the neighborhood pixels. Then average of the neighborhood pixels value will be 8.4. So the original value 7 is replaced by 8.4. That is shown in the next slide. This is 8.4 marked in blue color. Previously it is 7. Now it is 8.4. Now what we are going to use, again we have to change this and this, the remaining 8 elements. So what we have to do, again move the mask to the right side. This is first mask. Again we have to move this mask such that the next center pixel, that is 9, will be changed. Here also we are going to change this pixel value by average of the neighborhood pixel, same calculations. You see at the bottom, you will find out the calculations. It is multiplied and added, taking average. So here the new value will be 10.7. It is a calculated value. So the original pixel 9 is updated by 10.7. So like that, we can change. Again, we have to move this mask to right side. Again, this 11, that is the next pixel, will be modified. The updated values are marked in blue color. Like that, all the pixels are moved. Again, we have to move down. Again, the mask is moving down to one row so that the next pixel 10 will be updated. During the first 3 sliding of that mask, we updated the 3 pixel value, namely updated to 8.4, 10.7, 8.8. Next, we have to update the middle pixel value, 1058. Then after that, 956. So again, what we have to do, this space is again moved to this range, so that we can update the center pixel value 10. Same calculations. Updated value will be 10.3. Original is 10 and the updated value is 10.3. Like that, we can move the mask right side, then we can update. So this process will be repeated until all the original pixel values are updated by moving. This is called moving average filter also. This process is called moving average filter. This is called spatial low pass filtering. Same skipping, the calculation remains the same. No need to explain all the 9 by 9, 3 by 3, 9 values. This one is waste of time. Here, the entire 3 by 3, 9 original gray level values are updated by this blue color. So this is the comparison. Result of after averaging filter, the original image has this pixel. It is modified one. So the original pixel value will be changed, so that we can find out some filter. It is the filtered image, low pass filtered image. Obviously, it will be a blurred one only, but we can do some process by having this moving average filter, so that the original pixel grayscale will be changed. It is only a simple example showing original image with a 3 by 3 low pass smoothing filter or average filter, whatever you can call it. Is called as averaging filter or moving average filter or low pass filter or smoothing filter, right? Right hand side is a smoothened image, but it will be blurred. As I said earlier, the original pixel value is updated, right? Updated by new one. Maybe we can find some blurred image only. So can we use the same 3 by 3 mask? No, we can use a 5 by 5 mask also, so that we can use only one mask or one process at the time. No need to move the filter. If you use a 5x5 mask filter, then this is the output. Here also the smoothened image will be dull with respect to the original one. But anyhow, where it will be applicable, the pixel quality will be smoothened. It is spread over the entire image. The output of this spatial filter has one drawback of blurred image. So the mask weight value, we can say that the previous we can take 1 by 1. So the average is 3 by 3 9 elements. So totally 1 by 9 is divided. Or we can take this weight also 1 by 16. Like that, the pixel grayscale is changed with this value 1 to 1, 2, 4 to 1 to 1. That only you can take. The thing is, the average, the total values will be divided. That is average. That is a 60. So depending upon the weight values what we have taken, the output will be changing. If you look into the topmost one, 3 by 3 mask filter, we have this image. This is another image. I tried to complete this image enhancement alone. I think it is not possible to complete segmentation compressions. The time is 12 o'clock. But anyhow, be patient. I try to complete this enhancement within a couple of minutes. Sir? Karthikeyan, sir?
Yes, sir.
To which time, sir, we can take, sir?
Okay, sir. Okay, sir. Take a few minutes. Yeah, sure.
Okay. Okay, sir. If you have any time limits, you mention. Otherwise, I will complete it. No issues.
Oh.
So this is the second technique called high-pass filtering. It's high-pass filtering is another image enhancement technique. When compared with the previous one, we have done the spatial filtering in terms of average of the neighborhood pixels. Here, what we are going to is just we are taking the gradient of the neighborhood pixels. Gradient means the derivative. So where we use the high-pass filtering, wherever we have the edge detection, edge or border detection, then we can use this high-pass filtering. Suppose one pixel is suppose 0, another pixel is 1, for example. Between 0 and 1 grayscale, there is no much difference. You got it? Almost equal. See, the entire grayscale is 0 to 255. If one pixel having the gray level 1, another pixel is gray level 2 or 3. The minimum variation is very minimum, very small. Or if it is same, first pixel is 1, second pixel value is also grayscale 1. If we take the difference, 0. So there is no edge is found between this pixel value and this pixel value. Right? If neighborhood pixels are of same grayscale value, then there is then there is no possibility of finding the edges, right? So suppose if one image is having a pixel value 10, for example, neighborhood pixel is having the pixel value 225, for example. Larger variations will be there between 10 and 225. So definitely there will be a lot of changes between this pixel and that pixel. That is called the edges, boundary. You got it? If all the neighborhood pixels are same pixel value or slightly variable, then there is no difference. If we have high variations with respect to the pixel value, then we can find that there will be some edges or border will be present between the pixel value 10 and the pixel value 225. Large of difference. That difference is applied here. That is why it is called as a derivative. It is just a differentiation. Finding the difference of the gray level of the 2 pixels. Right? So that we can find out the borders or the edges effectively. So this is one example for taking the mask. It is called Laplacian Mask. Laplacian Mask is we are taking the second degree derivative, dou squared f by dou x squared. Right? Here for the example we have shown 4 masks. The top left mask is having that intensity -4. The neighborhoods are placed with this gray level 1, 1, 1, so that the sum of all the pixels will be 0, -1. This is also another mask, a 3 by 3 mask having center pixel value is negative, so that the neighborhood pixels are positive 1. The condition is sum of all these pixel values should be equal to 0. Why we are taking negative? Suppose this is -1, -4, right? -4, actually the grayscale does not having a negative grayscale, gray level value, 0 to 255 only. Suppose -4 means it is meaning that it is 0. So between -4 and this adjacent pixel, neighborhood pixel, lot of difference is there, right? So definitely there will be a edge between or boundary between this pixel and this pixel. Again, with respect to -4, this and topmost, this is larger variations. But between -4 and 0, as I said earlier, -4 is equivalent to 0, since no grayscale is specified in a negative side, only positive side, 0 to 255 only, right? So this is same. But with respect to this, it is different. So with respect to the 4 neighborhood pixel, it is identified as a edge. Similarly, if we take this kind of images, mask, -8, all the 8 neighborhood pixels are different. 1, 1, 1 means definitely there will be a tremendous reduction of edges or images. The bottom is just reverse. Bottom mask, the center pixel will have the positive pixel. So the neighborhood pixels are negative. Here 8, it is -1. The only difference is the neighborhood pixel will be differed with satisfactorily. That is the mean. Then only we can take the slope. Actually, here the differentiation is applied derivative. Where we take the differentiation, if we have a constant or no change in the gray level, there is no slope. We cannot take the differentiation. Differentiation of constant is 0. If we have a high variation slope, if we apply the gradient or the differentiation, we will have some output. That is a rate of change of that line will be calculated by slope. So for that only we are applying this Laplacian filter. Okay. So this is a typical mask used for the high pass filtering or Laplace operator. Here also the calculation of each pixel is same. So the calculation is not repeated again. Just here also we have to move one particular mask over the entire image. Then the calculations will be same. So if we take a mask having this size -8, negative pixel at the center and positive are at the boundary, then this is the original pixel. Now we see the output of the high pass filter. Wherever we have the edges, it is detected. Right? That's why it is called sharpening or high pass filtering. So low pass filtering is like an integration. High pass filtering is like a differentiation. So low pass filter will give the overall image. If we have a group photo, suppose 100 persons are standing in a single snap. If we want to find out the overall 100 persons, then we can go for low pass filtering. My objective is to detect all the 10 persons image. So if we want to focus on particular person image, then I can go for high pass filtering among the 100 persons group photo. If we want to find out one particular persons, then I can go for high pass filtering, image sharpening. Okay. So in low pass filtering, my objective is to see the entire 100 persons. That's all. The quality is blurring only. There is no doubt in low pass filtering. The overall image we can visualize. We can identify group photo, 10 members, 100 members are present. But the quality of individual persons is not up to that level if we apply a low pass filter. So our objective is to detect the entire 100 persons photo. So in that case, we can apply low pass filtering. Wherever we have the edges or fine details about one particular object or image, we can apply high pass filtering. This sharpening. Here also we can change the size of the mask. Instead of 3 by 3, we can apply a 5 by 5 or 4 by 4, whatever we can take. And the next one is high boost filtering. High boost filtering means it is the amplified form. So the original image minus the low pass filter is the high pass. Normally, low pass filter is simply original image subtracted from high pass filter. Or high pass filter is original image subtracted from low pass filter. That is the basic equation. So high boost filtering is, so this is your original image which is amplified by the amplification factor A. A is a scalar, so constant. Then this is given to the subtractor here. This is output of low pass filter. So A into f of m, mn minus fn means that the original image is magnified by the magnification factor A or scalar factor A minus the low pass filter output is our high boost filtering. Okay. That is the high boost filter. Where A is A and the high boost filter equation is this is formula A into original image. Here original image is represented by f of f comma n minus low pass image. Here low pass image is the output of this low pass filter f of m comma n. So this is the high boost filtering. So wherever we need the magnified form of the image, then we can go for high boost filter. This is the original image of the rice. If we do the high pass filter, then the image will look like this, so that the edges of each rice as well as the internal structure will be fine-tuned, since the variations is clearly focused in the high boost filtering, high pass filtering. So the bottom image is the high boosted filter image. Now you see the difference. If you look into the original image, the rice is white in color, but here it is boosted with the amplification factor A, so that it will look like this expression. Got it? So the inverse, or if we subtract the original image, this image, by this high pass image, we have the low pass image, right? That low pass image is magnified, so that we will get the high boost filter. Another filter will be used in the spatial domain called nonlinear filter. Actually, the low pass filter is a linear filter. Laplacian is also linear, but if we take a gradient, it is linear. If you take Laplace, that is a second order derivative, it will be a nonlinear filter. Then a nonlinear filter, we have different types. We see only one, the median filter. I will show the example with this. We will finish that enhancement. This version for 5 minutes, I will cover. So median filter, what we have to do is just same procedure. Just we can take the median value of the individual pixel, right? As I said earlier, once the picture is given, then we can extend the top and the left picture in order to extend the neighborhood pixels. So this can be done by two ways. In the earlier, I used zero padding. The same thing will be applied using the pixel replication also. See, in the left side, I have these pixels 4, 3, 5, 2. In the top and bottom, we have this one. Below this, we have the neighborhood pixel. Right side of this, we have neighbor. So this can be ordered by zero padding. What we done in the previous slide. But the same can be applied using this pixel replication also. So we see both types here. Median filter, just we have to take initially empty mask having 3 by 3 size. Zero padding is again similar. This is the original. This is the image after pixel replication. What we did in the pixel replication is the original is 4 by 4 matrix 4, 3, 5, 2. This will be extended in the left side. This is pixel replication. No change in the inside the pixel. Only at the boundary, 4 siders, just we can extend. This 4, 3, 5, 2 will be placed here, 4, 3, 5, 2. Again, this 2, 3, 5, 6 is the original pixel. It is again replicated here, 2, 3, 5, 6. Here 1426 is the original pixel. Again, right side it is extended. That is called pixel replication. So top also it is replicated. This is 443211. The same pixel is replicated at the top. Similarly, at the bottom also it is replicated. This is the pixel replication. So why we are doing is just we have to find the neighborhood pixels for the corner image, right? Or in terms of zero padding also we can do, like the previous example, the zeros are ordered in all the boundaries. Now we see the median filtering using this pixel replication of original image. Just we are placing a mask 3 by 3. 3 by 3 is an empty mask. Nothing is filtered. Nothing is filled inside this 3 by 3 mask, right? The empty mask is moved over the 3 by original image. That is this region, this block region. We have to find out the here in the 3 by 3 mask we have 9 elements, right? So these 9 pixel values are 4, 4, 3, 4, 4, 3, 3, 3, 1. That is this one. 4, 4, 3, 4, and 4, 3, like that. You can 3, 3, 1. These 3 by 3 pixel gray levels are measured here, marked here. This will be arranged in ascending or descending order. Finding the median value, like normal mathematics. So the original value here it is written in descending order. So the median of this value is again 3, which is marked in the circle. That 3 will be placed in the original image. The original pixel has the value 4. That is replaced by the median value of the mask. So it is updated by 3. See this complete original value here it is 4. Here original value it is updated by 3. What is 3? How we are getting 3? The median of these pixel values. Similarly, the moving of the mask is straightforward, similar to the previous process like that. The median value of all the pixels after each time after movement of each mask is taken, then the median value is calculated. Then that median value will be updated in the original pixel value. That is this one. So this is the final output of median filter for zero padding. The left hand side is for same thing. This is given here. By applying this median filter, median value of the neighborhood pixel, we can do some processing. That is, this is our original image of I. This is corrupted. The median filter will give the better output by applying this median value of each pixel. Probably it removes some drawbacks are there. It removes some details about the original object, original image. It will remove some pixels. The signal dependent noise is there. As I said earlier, by removing the original pixel, it will introduce the noise. So noises and the signals are dependent. But anyhow, it will be find some applications in image processing. So with this image enhancement is over. Next we have 2 more topics called image compression and segmentation. Now it is 12:20. Sir, can I continue or we can conclude, sir? At the end, sir.
Sir, okay, sir. Now you can conclude, sir.
Since afternoon also they will have the session, right?
Yes, sir. 120, sir.
Okay. Actually, image compression and segmentation is a left out one. It is not possible to complete. Okay. In future, suppose if we conduct any MDPs, then we will cover this one.
Sure.
Okay. If you have any queries, then now we can ask, sir. Please.
Participants, any queries?
Everybody in the waiting for lunch.
Participants, Any doubt? You have any doubt, clarification you ask to Dr. Sasi, sir?
Because of the time boundary, I have taken very fast, I think so. Whether how many of you listen properly or not, I am not sure. Since I rushed very fast, since it is taken from remote online mode, there will be some gap between the listener and speaker, I think. But anyhow, we will try to take the classes effectively. What are the drawbacks we faced, then we have to rectify it. That is the thing. So feel free, ask your doubts, no issues. Or you can put it in the chat box. I will try to clear your doubts. See, in the example, I have taken only the biomedicals and some images only. I am not taking any electrical oriented images. But anyhow, this is the basic concept. We will extend this concept in machine learning and deep learning also. In case of particularly micro grid, smart grid. Smart grid, you can apply this machine learning and deep learning algorithm, particularly related with artificial intelligence. So that basic concept about the image processing you must know. Based on the image processing only, how we are extracting the image attributes or the parameters, how it is given to the artificial intelligence algorithm. That is, so for that we must know the basics of digital image processing, irrespective of the engineering domain, whether it is electrical or civil or mechanical, whatever it may be. But the image processing is a main important thing. The applications we can take anything, either biomedical image or electrical or civil based image we can take. The segmentation and the comparisons are a simple part only, but again it will take minimum half an hour to 45 minutes, but it is not possible. These are the references I have taken. It is taken from the standard book Gonzalez and Richard book. And another book using MATLAB. Since it is related with image processing, we can use the simulation of the images or the enhancement. Any methodology we can simulate with the MATLAB software. For this, you can refer this book. Gerard Blanchett and Marais Charbit is the standard textbook, in which they have given numerous examples of MATLAB. These are the list of references I have used. Sir, at the end, sir?
Yes, sir. Yeah.
Yes, sir. Yes.
Yeah.
Or even not now, if they are asking any queries in future, you just post the queries, sir. Actually,
Yes.
I will clarify the queries.
Okay, sir. Okay, sir. Okay. Thank you, sir. Thank you very much.
Thank you, sir.
Okay, sir. Nice presentation, sir. Very clear. Yeah.
Okay, sir. Okay. Actually, if I complete all the remaining two tops, I will be satisfied. But time constraints, sir. Okay. Yes, sir.
Okay. Yeah. Thank you, sir. Thank you, sir. Thank you very much, sir.
Okay, sir. Thank you, sir.